For the last 5 years, tech giants sold you a lie. They claimed that building a superintelligent AI was simply a matter of buying enough microchips and feeding them the entire internet. Today, that strategy has crashed into a wall. The raw web is exhausted, polluted, and legally toxic. The real race is no longer about who has the biggest compute cluster, but who controls the invisible filter. We have entered the era of data exhaustion. The raw, unguided internet can no longer train the next generation of systems. The advantage has shifted from the billionaires buying graphics cards to an elite class of silent architects. These are the data curators, taxonomic engineers, and mathematicians who are quietly rewriting the boundaries of what these systems can actually do. To understand how we got here, we have to look past the marketing hype of parameter counts. For years, the industry operated under a brute force assumption. The larger the model, the smarter the output. But this assumption ignored a fundamental structural flaw. When you train a model on raw web-scraped data, you are not feeding it a library. You are feeding it a digital landfill. By mid-2025, the industry hit a quality plateau. Models trained on petabytes of raw text began repeating their own errors, hallucinating facts with absolute authority, and collapsing under the weight of their own training data. More compute only made them fail faster and at a higher cost. The realization was brutal. A model is not defined by the size of its neural network, but by the mathematical cleanliness of its training pipeline. Think of training a model like forging a precision aerospace alloy. If you melt down a mountain of random scrap metal, you will get a brittle, unpredictable cast. But if you carefully isolate trace elements down to parts per million, you get a material that can survive space travel. Data curation is that precision refinery. It is not just about deleting spam or filtering out offensive language. It is a highly disciplined mathematical process. Curators must design custom taxonomic structures, build automated semantic filters, and verify the physical provenance of every single token. If a single unverified stream enters the pipeline, it can distort the entire mathematical space of the model, rendering a multi-million-dollar training run completely useless. We saw this play out in a critical evaluation of state-of-the-art models like Llama 3, Codestral, and DeepSeek R1. Researchers tested their ability to identify security vulnerabilities in software code. These models are massive, trained on billions of lines of code. Yet, when tasked with identifying real-world security flaws, their raw size meant almost nothing. Their success was entirely determined by how well their training data mapped to a structured classification system known as the common weakness enumeration. Models trained on raw, uncurated code repositories failed to spot critical structural defects. But when the training inputs were restricted to a highly structured, closed-world taxonomic framework, even smaller models outperformed their massive competitors. The implication is clear. Raw size cannot compensate for structural chaos in the training data. This bottleneck is even more severe when we move from text to the physical sciences. Consider machine learning models used to design new battery chemistries or aerospace alloys. In this domain, a single hallucinated data point is not just a minor error. It is a physical impossibility that can lead to explosive failures in a physical lab. To train these machine learning interatomic potentials, curators cannot rely on scraping research papers. They must map what is called the structural space of atoms. Every training sample must represent a physically stable state of matter. Curators must mathematically filter out physical anomalies and construct highly precise chemical training sets. If the dataset has a single gap in its structural space, the model will fail to predict how a material behaves under pressure. Here, data curation is the difference between a breakthrough material and a wasted decade of research. The stakes reach their peak in clinical medicine. Building an AI diagnostic tool requires more than teaching a model to read medical text or recognize patterns in X-rays. It requires multimodal synergy, aligning a patient's imaging files, genetic sequences, and historical health records into a single, cohesive timeline. This is a curation nightmare. If a curator aligns an MRI scan with a genomic profile that was recorded even a few weeks out of sequence, the model can associate the wrong cellular mutations with the wrong physical tumor. A mistake in the curation pipeline does not just lower accuracy metrics. It leads to misdiagnosis. In medicine, The critical engineering happens long before the model is trained, in the silent work of aligning disparate, messy, and highly sensitive human data. But the challenge is not just about cleaning honest mistakes. It is about defending against active sabotage. As the industry moves toward distributed training and federated learning, models are increasingly trained on data gathered from decentralized networks. This has opened the door to a devastating vector, data poisoning. In a Byzantine attack, a malicious actor intentionally injects clean-looking but mathematically toxic data into the training stream. To a standard filter, this data looks normal. But once integrated into the model, it creates a hidden backdoor, allowing an attacker to bypass the system's security controls with a simple trigger phrase. To survive, curation pipelines must now employ advanced mathematical resilience filtering, acting as active security firewalls to defend the model's neural weights from being corrupted from within. The era of training models on the unguided internet is officially over. The companies that continue to chase parameter scaling at the expense of data integrity are finding themselves stuck behind an invisible wall of diminishing returns. The future does not belong to those who build the largest neural networks or buy the most graphics cards. It belongs to the silent architects, the domain experts, the mathematical curators, and the rigorous taxonomists who understand that a machine can only ever be as intelligent as the structure of the information we give it. The magic of artificial intelligence was never in the code. It has always been in the quiet, disciplined curation of human knowledge.